Today, we will be talking about Minkowski and Penrose spacetime diagrams. What you currently see in front of you is a Minkowski spacetime diagram, which was created by Hermann Minkowski, one of Einstein's professors. This graph represents four-dimensional spacetime, a two-dimensional way. The graph has space, aka position on the x-axis, and time on the y-axis. The x-axis represents the present, so anything above is the future, while anything below it is the past. The line graphed on the Minkowski diagram is often referred to as the object's world line, as it represents the position of an event or object throughout time. Like a normal position time graph, a steeper slope represents a greater speed. So the CERN linear accelerator would have a steeper slope than a car. The unit traditionally used on the x-axis is light seconds, which is 3 times 10 to the 8 meters. Because this is such a large magnitude, a snail and a race car would have an incredibly similar slope. The events that can happen within these cones can affect the object, which is where the two lines intersect. The top cone represents future events, while the bottom cone represents past events. Events that are within these time cones are considered to be time-like, while events outside of them are considered to be space-like. And events that happen within zones such as these, where my mouse is, are out of the time cones, so they can't affect the object. So let's look at an example of how to interpret a Minkowski spacetime diagram. So I want you to imagine that the blue line on the x-axis is a woman with a weapon, and she's running at the victim, who is represented by a purple square. The woman attacks at point B, which is where the Good Samaritan, represented by the green square, sees this happening and sends a warning. The victim unfortunately dies at point C. Now, you must be wondering, well, why did the warning not work? Well, we need to consider the light cones of each event. Point C, where the death of the woman is, it's not in the future light cone of B, the warning. So the warning is not able to have any effect on the death. The warning is also not in the past light cone for the death event. At point D, the victim would receive the warning, but because that is after where the victim was killed, it wouldn't work. So now let's look at a bit of a real life demo. So what you're about to see is a bead which represents event, and some string which is representing the light cones. So let's look at that. So then the yellow bead represents the event, and if I play around with events, the light cone represented by the string, that is the space and time of the bead. But if I don't do anything with those light cones, nothing happens. You can also see that if I play around in one light cone, it'll affect other events within that same light cone, which can show us how events within a light cone can affect other events within them. Let's consider a bit of math that we can do with this. So this graph can be used to measure the distance between two events in space-time. The distance is referred to as the space-time interval or proper time. The equation shown on the screen will allow us to solve for this. This is very similar to the structure of the Pythagorean theorem, because they're doing a similar thing, finding the distance between 2 points. The reason time is negative is because this equation operates under the assumption that the speed from one event to the other is less than the speed of light. This equation applies to the entire diagram, assuming that there is nothing else that's affecting it. If something is happening at light speed, the two events will be along the edge of the light cone and will have a positive proper time. If one event occurs inside the light cone, the other one occurs outside of it, the proper time is considered to be negative, which implies that it is impossible to go from one event to the other. There are a few shortcomings of this model, though. For example, one is that time is infinite. This diagram cannot logistically show it. Another fault of the Minkowski spacetime diagram is that it cannot properly demonstrate how black holes behave as they warp time and space. To better explain events such as these, the Penrose diagram must be used.
A black hole warps space-time. Therefore, time always moves in the direction of the singularity, and space moves parallel to the singularity. The behavior of light is also affected when it comes into contact with a black hole. This is where the Penrose diagram comes into play. This diagram is essentially a manipulation of the Minkowski diagram, which places this diagram into finite space through conformal transformation. The angles in this graph are still preserved, however the lengths will differ. This effect is comparable to a photo taken with a fisheye lens on a camera. On a Penrose diagram, The y-axis represents time, and the x-axis represents space. Light always travels at a 45-degree angle. The corners of this graph represent infinite time and space. When approaching the corner on the y-axis, something becomes more time-like, and the corners on the x-axis, something becomes more space-like. When approaching the borders of this graph, however, something becomes more light-like. A black hole can be depicted on this diagram at a 45-degree angle. When something approaches the black hole, more and more of its light cone is inside the event horizon. However, the portion that is not represents the chance that the object has to escape. If the entire future light cone is inside the event horizon, the only possible method of escape is to move at a speed faster than light. All future events terminate at the singularity of the black hole itself. So this is where it gets way more complicated if you thought that wasn't enough. Over many iterations of this basic diagram, multiple scientists have expanded the diagram using a variety of complex calculations. The expansions of this diagram predict time reversal versions of a black hole. This means that if time were flowing opposite to the way we perceived it, a white hole would exist. This also suggests time reversal is fundamentally possible. This theoretical white hole is similar to a black hole, except for the fact that it has a force opposite to gravity and forces objects outwards. This also then creates the idea of the anti-horizon, leading to the theory of a parallel universe. This is a universe with physics that functions similar to ours, running completely in parallel. When traveling through the event horizon of a black hole, if somehow it was possible to escape, you would reach a new universe through a wormhole that is completely different from ours. This wormhole, however, predicts the idea of the antiverse, a universe completely disconnected from our own and unreachable by any method. In this antiverse, time would flow opposite to the way that it flows in our universe. But of course, we won't know if any of this is possible, and many scientists believe it isn't. At least for now, it is impossible to travel anywhere even close to the speed of light to test this out.
Wow, Eric, that's really interesting. But I've got some questions for you. So, what are some problems caused due to the warping of space-time by black holes, which we can see on the Penrose diagram?
The warping of spacetime by black holes, as shown in the diagram, implies that time slows near the event horizon. Light cones tilt inward as the object nears a black hole, meaning that all paths lead to a singularity, making escape impossible.
Wow, that's cool. Do you have any questions for me?
How do light cones help in understanding the speed of light as a universal speed limit?
Well, due to the 45-degree angle paths that light can take, it can be seen that nothing can travel faster than light as this object would then be outside of the light cone, and not in the future or past the frame of reference, and therefore not observable. Eric, just one last question for you. What does Penrose diagram suggest about the relationship between space and time as something approaches a black hole?
Time becomes more space-like, always moving towards the black hole, and space becomes more time-like, as moving towards the future always leads to the singularity.
Well, thanks, Eric, for all that information, and thank you guys for watching the video. We hope to see you soon.